All right, our first talk is from Houri-Christina Tarazi, who's going to tell us about on the finiteness of supergravity landscape in D equals 6. Take it away, Houri.
Hello, thank you for the invitation. Yes, I will be discussing the finiteness of supergravity landscape in D equals 6 and 8 superchargers. Firstly, I would like to just give a little of an overview of where we stand on supersymmetric theories as far as the Swampland is concerned. So let's start by understanding first what is the Swampland problem, what are we trying to do? So what we're trying to do is answer the following question. How do we distinguish between apparently consistent quantum field theories that appear in the low energy of quantum gravity and those that cannot? We know very well that not all of them can be coupled consistent to gravity. So we want to find consistency conditions that can distinguish those. So those that are consistent with gravity, we say they belong to the landscape, and those that are not in the swampland. Okay. The next question, natural question, is where does the string landscape fit in here? So the String Lamppost Principle would want us to say that those overlap, the string landscape and the supergravity landscape overlap. However, we don't want to just take that approach and believe it. What we want to see is go from the supergravity landscape and reach to the string landscape by consistency conditions, if that's possible. So that's another question to be answered. Okay, so the very basic idea is that can we use some fundamental ideas that have to be true for quantum gravitational theories in order to construct such conditions? Well, yes. So we can start by very simple arguments. So unitarity. Every quantum gravity needs to be unitary. Anomaly cancellation. All gauge gravitational mixed anomalies should cancel in a consistent theory. The next one, very well known also, is the completeness of spectrum hypothesis. So we assume that it says, basically states that in a quantum gravity, for any p-form gauge field, every charge p-1 brane state should appear in the spectrum. This is first proposed from Polchinski back in 03. It was then from Bax and Seiberg. They gave a nice black hole argument, and then later Harlan or Guri from ADS-50. So it's well-established conjecture. Then we have the cobordism conjecture, stating that all the cobordism classes in a consistent quantum theory of gravity must vanish. This can be thought as a generalization of completeness of spectrum and no global symmetries kind of arguments from McNamara and Vafa in 19. And one more is the distance conjecture, that in a quantum gravity at infinite distance in the scale of moduli space, an infinite tower of states becomes exponentially light, proposed by Guri and Vafa in 2006. There are many, many more Swampland conditions, and this is not an exhaustive presentation of those. It's just the ones that are useful for us in order to understand where the supersymmetric quantum field theories stand in between the landscape and the swamp. So this is going to be my toolbox. But let's kind of review a little bit where we stand in general. So for 32 supercharges, we can start from, from 32 supercharges, we have the low energy limit being completely determined by supersymmetry, and it's unique except in 10 dimensions. So for 11 dimensions, we know very well M theory. In 10 dimensions, we have type 2A and type 2B string theories. And for D less than 10, these are circle compactifications. So this is very simple evidence, at least for the String Lamppost principle, that the landscape and the string landscape match nicely. Now let's go down to 16 superchargers. Well, for D equal to 10, this is very well known that anomaly cancellation allows for these 4 types of gauge groups. Back in 2010, Adams, DeWolf, and Taylor have a nice argument using anomalies and invariants to show that the last 2 are not consistent. Recently, Kim, Shi, and Vafa also found an argument based on string defects and completeness of spectrum, really, to exclude those theories. And we're going to utilize those tools. So for D less than 10 now, all are non-chiral except 62,0 theories, and this can be realized in type 2B on K3. Now, for non-chiral theories, the rank of the gauge group we showed with Cumrun Vafa that is bounded by 26 minus d for any gauge group. For example, when you have 4d n equals to 4 super young males, the rank cannot, at least the rank for more than 22 belongs to the Swampland for Minkowski bucket. Okay, so then we go on and we're like, okay, what kind of ranks are allowed in string theory? So you can see here, for example, these are, oh no, okay, this one. So these are the ranks that show up in string theory. So we have rank equals 1, 9, and 17. This is can be seen by M theory in the Klein bottle or type 2B on the DDP background, CHL string heterotic on S1. So it was, we also know though from this paper that actually these are the ranks that should appear because of anomalies, which is quite interesting. So this is also some form of evidence towards the lamppost, even though we don't know the exact groups that can appear. Now in d equals to 7, these are the ranks that appear in string theory, but Montero and Vafa have a nice argument saying that at least it has to be odd, though not excluding all of them. Okay, so then what type of gauge group can appear? This is another sort of SLP question. We know that in 8 dimensions, not all the gauge groups can appear. For example, this type cannot appear. The first two were shown not to exist because again of some global anomaly, and recently using 3-brain probes, G2 was also got out of the way. So we're closer here. So this is pretty nice. So now going down to 8 supercharges, things start getting a little bit harder. Thankfully, the first theory, 6 dimensions, has lots of anomalies to constrain it. This has been studied a lot by Morrison, Kumar, Taylor, and many other papers. They worked with collaborators, and they utilized a lot the anomalies there, but of course there's still many infinite families of theories that appear here. Now, an extra ingredient recently came up is from Kim, Shion Vafa, and Lian Weigand, where the extra conditions basically are extended objects. So you have completeness of spectrum, which we're going to utilize here, and you have these extended objects, which are going to put more constraints. So today's talk, we're going to basically focus on this and try to show the finiteness of massless modes with this type of theories. Now, for d equals to 5, I'm just going to mention, and I'm going to really discuss it because we did some work with Sheldon Katz, Kim, and Cumrun Vafa on this. Of course, it's much harder because there's no bulk anomalies here, but in a similar kind of mindset to what I'm going to use today, you can have certain arguments of the form like if I have a U1 graviphoton times a gauge group G that Higgs is to the quintic, the rank is bounded. And there is also a nice bound on the Higgs branch relatively to some d cubed, which is the intersection of some divisor class associated, you can think of a black string. So there's some form of at least bound, not generic, but some constraining the whole quantum filters. So today we're going to focus on these 3, as I previously mentioned, the first 3. So let's have a review of 60 n equals to 1 supergravities. So there is 4 types of multiplets that come in here. This is the supergravity multiplet, tensor multiplets, vector multiplet, and hypermultiplets. And of course, this is a chiral theory. It suffers from anomalies, and an extension of the Green-Schwarz mechanism by Sagnotti is here to save us and cancel the anomalies when the anomaly polynomials factorize of this form. Okay, so they depend on some vectors, A and B, in R1, T. And the anomaly conditions basically are here and here. Okay, this is, for example, the number of hypermultiplets, number of vector multiplets, and tensor multiplets. So they're sort of constraining for the set of like quantum field theories. Okay, so, but as I said, they still leave an infinite number of theories that could appear. And this is not something we would like it to be true. So let's focus on the first two types of theories, supergravity multiplet and tensor multiplet. So what does completeness of spectrum tell us? At least some stronger version. So that we will have some BPS strings charged under the two forms, the two for fields, which will have some 0,4, they're going to be half BPS, so some 0,4 SCFT in the low energy. Now, unitarity of the string worldsheet, again, we want theory to be unitary, not just the bulk, but the worldsheet as well, will require that the central charges, so we have the bulk gauge symmetry, it's going to show up as a flavor symmetry, so it should be constrained by the central charge on the left. Okay, and lastly, again, anomaly cancellation. So there's a well-known anomaly inflow. So once you put the defect, the Byakian identity basically has an extra corrections. So once you plug this in, you can see that there is some anomaly inflow towards the string. Integrating out the 4 dimensions, you get basically an I4 polynomial, which should be canceling with the worldsheet anomalies. Okay, so this is basically this condition. The worldsheet anomaly polynomials depends on the central charges and the levels. So basically we can read off, this is basically what was done by Cumrun Vafa. So we can read off the C left, C right central charges with respect to a string of charge Q and our vector A, which we had earlier. And then we have the level of the gauge group being Q dot BI, and the level of the SU2R, so we have an SO4 transverse symmetry, which is basically SU2L and SU2R, and this is the SU2R becomes the R symmetry. Okay, so this is really a review of what was discussed in those papers. Some other extra conditions that have been discussed in the earlier papers by Taylor and earlier with Sagnotti, some of them. So we have that the kinetic term should be positive. The metric should be positive on the moduli space. J squared should be positive. The tension should be positive of the string. This is, of course, associated to having completeness of spectrum. And lastly, one more condition, which is believed to be true, is J dot A being positive, although not rigorously proven. Okay, so these conditions can be summarized as this. So you can have Q squared greater or equal to -1. And all these other conditions should be true for a consistent theory. Great. So now we want to add an extra ingredient. So what is the next ingredient we want to add? So we have massless matter in hypermultiplets in the bulk. And we say that this corresponds to relevant or marginal vertex operators on the string. So basically you can think of this that Higgsing the bulk gauge group should deform the flavor symmetry on the worldsheet. So whether the argument can be extended to not being Higgs, not being able to Higgs by having some marginally irrelevant deformation. But the point is that the conformal dimension of that operator should be less or equal to 1. Okay, and since it has to be less or equal to 1, we have a primary, and we know the very well-known formula for the highest weight representation in a Kac-Moody algebra, where the weights of the highest weight is bounded by the level. So this gives us, these two give us a nice relation constraining the matter of such theories. For example, one theory that cannot be realized on F theory for any n was the SUN n-8 fundamentals and 1 symmetric matter. The reason was that you couldn't map B basically to some effective divisor. Okay, so we would like to exclude this. So let's pick a basis. So we can pick some basis of this form and A and B vectors, and plugging this in and making a minimal choice of Q. So basically what I mean by minimal is that I want to choose a Q that satisfies these relations, but also minimizes them. So minimizes the central charge. So in that case, we can find a Q such that K is equal to 1. But obviously now we are bounding the highest weight by 1, and that's not true for the symmetric representation. So this theory should not exist for at least that choice of basis. So this is pretty nice. Okay. So I just want to also say that the first condition is also a nice condition, but it didn't become very useful in our study. And the reason is that it's mostly true for a simple matter like fundamental symmetric antisymmetric. You need to go into more exotic representations to have it be bound, having be a strong bound. And this could be useful if you are really trying to either classify the supergravities or trying to answer the SLP type of questions. But here we want to focus more on finiteness. Okay, so let's see. So as we said, the SLP wants us to have finitely many consistent theories coupled to gravity. So we can now remind ourselves what was happening in basically a series of papers with Komar, Mars, and Taylor that showed up back in 2009, 10, that they started trying to understand this better, like how many theories exist. So for non-abelian theories, so here I will just focus on the non-abelian theories, for a fixed T and the dimension of the gauge group being finite, then you can basically, they showed by careful analysis of gravitational anomalies that those theories are finite. So I cannot have an infinite, so I cannot have an infinite number of those. This is for any T. Now, when we go down, now we want to ask, what about an unbounded dimension? So if I have a gauge group of unbounded dimension. So they very nicely also show that in this case, so for example, for one gauge factor, these theories do not show up for T less than 9, they don't exist. These ones are not infinite families for the first simple reason, this column is H minus V, and H minus V needs to be less than 273 in order for gravitational anomaly to be satisfied. So, and basically here is restricted, so it cannot be infinite. So we need to have combinations of gauge groups in order to be finite, at least the H minus V. And this kind of gauge group, for example, this kind of gauge groups showed up in those papers for infinite n. So n could be arbitrarily large. They showed again that these for T less than 9 cannot appear. So here we want to extend these arguments to satisfy for all T greater or equal to 9. Okay, so, the first two theories is, let's say, are these. We can start from these two guys that do appear for T greater or equal to 9. So we can again choose some bases, a squared, b squared. The combinations are a squared, b squared, a dot b are all 0. So b is actually proportional to a. So I can choose a basis again, omega, given by these vectors. Unitarity tells me that this relation should be satisfied for some choice of q. These are the relations I want q to satisfy, so I can choose a minimal choice. And by completeness, it should be there. Okay, so this gives me that the central charge is 8. This puts a nice bound on those theories, and only these solutions exist, at least for n less or equal to 9. They don't really exist, but at least we cannot disprove. But if we use also the matter bound that we had earlier, in this case, for the adjoint symmetric matter, we can see that all k equals to 1 cases are excluded. So basically we have less or equal to 5. However, we can't really disprove this, but that they exist, but at least from an F-theory perspective, this definitely cannot really appear because A and B are primitive. So really lambda would be 1 in the F-theory setting. So we would need some other means to show that these theories don't exist, but at least they're finite. Now let's move on to two gauge group factors. So for two gauge group factors for T equals to 9, you can actually show that these don't exist. So B1, B2 don't exist for this type of theories.
So, sorry, Houri, quick question. Why does B have to be primitive in the last picture?
In the F theory.
Why would B have to be primitive in F theory?
Isn't B in your paper, B is primitive in F theory.
I don't think B necessarily has to be primitive.
You showed it in the, right? Didn't you show it in the global what's the global paper?
You sure it has to be effective? I mean, positive. But
I think maybe I'm mistaken, but if I remember, I did it from memory, but
maybe
yeah.
it's for that, sorry, maybe it's for that particular matter content. It does need to be. I mean, because in general, it doesn't need to be primitive. But yeah, sorry, maybe I'm just forgetting that story. Okay.
Yeah, maybe that's this is just yeah.
Yeah, sorry, maybe for this class of theories for some, I'll have to remind myself of that. Thanks, I'd forgotten. I have to think about that.
It's not so crucial because the point here is not to try and construct F-theory models. It's more to like show the finiteness of the theory.
Absolutely.
And, if they can be constructed, it would be nice, but if they can't,
okay, thanks. Sorry.
Yeah. So let's look now for two gauge group factors. So we go on. So the first theory was studied by Cumrun Vafa, and they showed that n should be less or equal to 9. While the rest of the theories we are studying here, I'm not going to go through all the theories because they're pretty similar, but let's have a look, let's say, at the first one over here, SO 2n plus a times SPN. It's easy to show that for t equals to 9, these don't exist. And for t equals to 10, we cannot use the similar arguments before because solutions do exist. And we can find a solution of this form, including J. And unitarity now of the string worldsheet can give us some constraint of this type. We can choose again some minimal choice of charge and show that n should be less or equal to 1/2. And for these cases, basically, if you choose 0 or 1/2, you get SO8 or SO9 plus 1/2, which were studied for large T to exist in the Morrison-Taylor paper in 2012. So that's good. So these are finite too for those space. So a similar procedure can actually show that all these theories are finite, and that's what we do. You basically try to find a basis, and you show that n should be finite. So all these are finite, and for t equals to 9, actually they don't exist. We can actually do more and go on and find a larger class of theories. So you can have k simple factors of such infinite groups, which do not fall in the first category of having infinite factors because they actually have unbounded dimension. Okay, so you can have this type of theories, which also you can construct. You can also find solutions of this form, some general solution of this form, and show that they're actually finite. So these are also finite for a specific choice of basis. Okay, so this is nice. So now one thing that we should point out here is that we have in particularly chosen a basis. So in each of these examples, let's go back and remember. So we did show that all these and these and these and more gauge factors that you can construct, so you can show which theories can actually exist as infinite families. You can show that all of them are finite for a specific choice of basis. However, this might not be a unique basis. There might be some other basis coming up here. So generally, so you can have these unitary condition we discussed. And the condition that the level of the shear to left is positive gives us that basically central charges are bounded by 12 cubed squared. Now, if we make the assumption that there are only finitely many inequivalent theories for a given n, so n could be arbitrarily large at this point, but there's just finitely many solutions of those theories. So there's not an infinite number, let's say, of SU2 with 4 flavors. There's just a finite number of those. And we're going to assume that the string charge lattice is generated by BPS strings. Then the vectors A and B are actually independent of n. And the charge lattice of BPS states is also independent of n. Because, for example, giving a vev to a hypermultiplet and trying to Higgs the theory down to n-1 does not affect the inner product of the charge lattice. We also have to ask one more question. Okay, so that's one thing. So the charge lattice is independent of n, but what about the gauge symmetry could somehow be hiding from the worldshift? So can I have a situation where all Q's give me Ki 0? So that's actually not possible. It's not possible generically if you assume that the lattice generated by BPA strings, it just cannot happen. Then they will not generate the whole lattice because you have, for example, b squared, which is negative. But in our examples, we can do better. In our examples, we can actually find a Q, which is some combination of the J vector that should exist, and A, and construct some BPA string that has actually positive level. So at least for our examples, not generally, but this can happen. So we can be working under the condition that at least 1K is not 0. Therefore, this means that n, so at least one theory here, so at least some n is bounded by 12q squared plus 20. So, and we have that q squared is part of the lattice, so it's independent of n. Therefore, there should, since there's finite number of theories for each n, there should exist some minimal choice of q squared such that it bounds n. Okay, so basically, we know under these assumptions that n should be finite for this type of theories that we discussed in a basis-independent way. Okay, and just to finalize, to say one more word about what else is out there. So, of course, we have a very nice abelian theories of the form u1 to the n show up. And it was shown originally by Parkenthaler in 11 that those are mostly finite. And then Lee and Wagen made these conditions more strict. And we have that now in total, there's like a finite number of massless modes appearing here. However, we cannot still, although we have a finite number of massless modes in non-abelian theories as well as abelian, we cannot say that there's a finite number of theories in total, because there's this well-known theory over here, which has a different kind of infinity coming from the choices of the charges. So we would need a little bit more work to also get rid of this kind of theories to have full finiteness, but at least for the massless modes, we now know. Yep. Thank you. I think I stopped exactly on time.
Perfect. All right. Thank you, Houri, for the excellent talk. Let us all thank Houri using our clap emojis. And we first have a question and a comment from Yinan. Yinan?
Yinan?
So, man, let's see if he's... we cannot hear you, Yinan.
We can't. I'm sorry.
If you want to type it too, I can ask it. See, well, unfortunately, it seems like we're having some technical difficulties with Yinan's question right now.
I can answer on the chat later if he asks. Okay.
Yeah, perfect. All right. Well, let me ask a question. So this was, let's see. So Yinan typed his comment for the question. Wadi asked, the curve with a gauge group is primitive if the self-intersection number is 0 or negative.
Yeah.
Yeah.
That's what I had.
Thanks. Yeah, I realized that later as well, because I think in the case that Houri was looking at, it was a self-intersection -1 curve, in which case it's definitely going to be primitive. So yeah, thanks.
Okay, and my question was, this was a general analysis in 60, But there's this general expectation that most Calabi-Yau threefolds at least admit an elliptically fibered phase. So do you think your analysis can then be used to generally constrain most 5D theories under circle compactification?
5D is, I mean, okay, I mean, just putting it on a circle, it's really a 60 theory. But in 5D we have done, I mean, of course, the idea would be that we won't find theories in 5D, but in 5D is much harder. We did a little bit, like that's what I mean, I didn't talk much about it, but in the very beginning, I just, I kind of said because we studied 5D n equals to 1 theories. And of course, we don't have anomalies, so things are much harder, but you can have some form of constraints. So if I tell you, okay, take a gauge group, some random gauge group that Higgs is to the quintic or something like that, I can give you a bound on the rank of the gauge group. But, or on the Higgs branch here, I can, like, if you give me basically divisor, basically both depend on having a decubed. So you have a divisor, which is some form of black string, not exactly, we call them supergravity strings, but in some limit, they become black strings. And in those cases, like if you know that, I can give you a bound, but we don't know, let's say from Calabi-Yau also, what is the highest triple intersection of some Neff divisor inside the threefold that can give me that. If I knew that, then we would be done, but also mathematicians would be done.
Awesome, thank you. All right, I think we have time to do Yinan's question, then we should move on. The question is, what are the upper bound of T derived from these sequences?
Yeah, so I should have said it. So T is, let me see. So when you have K less or equal to 6, so you have less or equal to 6 Gates factors, it was 8 plus K. T, and in the other cases, it was 7 plus K for K greater or equal to 7. So that's the maximum you can get from gravitational anomalies, but only the last case, so 8 plus K or 7 plus K, are the ones that allow for solutions. We show that for less than that, actually, there is no solutions for A and B. So only the, when it saturates, the largest T is the one that finds solutions, and we show that they don't exist.
Okay, thank you very much, Houri. Let us all thank Houri again for an excellent talk.